So activation functions are very much helpful to activate a neuron, right? So it will be very much intuitive enough to activate a neuron either to be open or not, like that, right? Where we see various different neurons available lecture as such. You can look for linear neuron where the values which you pass in, it will be like that. So this is your weights and bias, and input value is your function. Whatever it can be from -1, -5 to whatever if it is the computation forms comes to be z, turns out to be minus negative value, it will be that, or positive, it will be that. Whatever the value you get from computation, the range of y value would be from -z to z. Okay, that is your linear neuron. At this point, your neuron will have a summation of whatever you get, right? When you use linear neuron. Okay, when you use binary threshold neuron, what happens is you put some threshold, either be at 0.05 or at zero point 0.3, zero point 0.4, whatever. You put some theta value. Greater than that, you turn that to be 1 or else 0, right? Got the point? When the z value, when you compute the z value, like summation of this one, summation of this value, summation of this value, and you get a z value with biases. Okay, with biases, it turns out that when the z value is above some threshold value, you turn that neuron to be 1. Else you turn this to, off it, like that, 0 or 1, binary threshold neuron. Okay, the range would be between 0 and 1. Okay, so stochastic binary threshold is where your value ranges from 0 to 1. You just specified that threshold to be at point 0.5. So what happens is at this positive z value, you get 1, else you get 0. Whenever it is lesser than 0 values, the z value which computed to be lesser than 0, then it will be like the value turns out to be 0, p value, probability value. Okay, that filtration comes in on this pooling. Right. So here whatever is there is your positive value. Here negative z value. Right? When you have a negative z value, the probability value will be like this, right? Either 0 or 1, y value turns out to be 0 or 1 based on this one. Sigmoid is another one where using this exponential function. Similarly, the exponential function would be for that also same. So at this point, what happens is it's same as your y value coming here and interrupting that. Yeah. So whenever z value is positive, it is above the threshold and the y value does not be 1. And when z value is negative, it is 0, like that. So more or less these are same, the y value and the p value. So it's like sigmoid is more being used. I guess some value y equation differs here. I would put in when I push it to you guys. I'll actually get you to the formula for stochastic binary threshold. So then I'll post the slides. So there'll be like not much significant difference between these two. And another one is your tan h. Tan h is one where uh, you get negative value. The range of values were from 0 to 1 in the earlier sigmoid, right? Here the values can be from 1 to -1. Okay, the values can be in the ranging of -1 to 1. So given that the z value which is being computed based on the summation of all those, if it is positive, the value turns out to be 1, else it will be -1, like that, the way the y value of that. if you use TAMH as your activation function. TAMH as your activation function, it can be in the range of -1 to 1. Okay. Yeah. And the another one is rectified linear unit. What it does is it filters out all the negative values. Whenever a negative value comes in as z, it will eliminate that and give you as 0, directly as 0. Whatever might be the value coming as -10, -5, whatever, it will give as you as 0 whenever the value is negative. And whenever the value is positive, it will give you 1 or z value, max, whatever the z value will give you. Now, I need to update this version. This would turn out to be z. I'll update this. Okay. The y value will be ranging from 0 to z. Whatever the positive value, let's say 5 is being computed, at that point of time, 5 value comes in directly. No issues with that. Right? Those things are there for activation function. Activation is being taken care at each neuron, probably at this neuron, and all those things. And then based on the range 0 to 1, 0 to -1 to 1, all these values will go into the next level. And then some activation function will be there at each neuron. Those gives you the result to the next layer, right? First we saw input associated with the weights, biases, and then it takes the activation function at this point, this neuron, summation of all these weights and all the things, which makes you z. Taking the z value, you understand that activation function either to be within the range of -1 to 1, 0 to 1, all those things. And then y value goes out to the another layer. That would be the output for that. That is how you forward propagate that. Okay. So let's say we understood the various activation functions. Probably like this one is very much highly used, sigmoid, tanh, and rectified linear unit. And I've included when to use what sort of thing in the link provided there. So reference link, when to use which one. Right? You also explore a bit so that you don't know. If I would have provided them, it would be like very easy. Okay, the next step is we are at this level. The activation has came in and you got the outcome from this. You got an outcome from this one. Okay, this will propagate to an y output layer, right? Either it will be active, or at that point of time this will be 0, or this will be 0, this will be active, like that. It's like 0 or 1, sort of. So class, as you can just say, as cat and dog classifier, where image, right? So when it comes to be the bulb is ignited for cat, then whatever the image you put in for the cat was ignited. These are the images vector. The image would be, let's say this is your image of a cat. This would be converted, this entire matrix would be converted into vector format and all those things. Then you feed it to your neural net, right? That is what you say pre-processing, and then passing into those things. Then based on the learning pattern, how cat looks like and what activation functions you use and all those things, you pass into that value, and then outcomes will be decided based on. But in realistic, you just will not have only one layer, you'll have multiple layers for it, and you will learn various patterns also. So just to understand, this is your input for a cat image pixels, and then based on that, it is deciding either it is a cat or dog. The y values comes in. Okay. Sometimes what happens is, right, sometimes what happens is you predict the value incorrectly. So for that, you need a cost function. Cost function, what it does is, it tries to quantify the error factor of a neural network. What it does is how well the neural network is performing based on the actual value versus predicted. Let's say the cat was, this was a cat, but you got the outcome as dog. right? You got the outcome as dog. Then your error predict error factor is your predicted minus actual value, or actual value minus predicted. This will be the absolute stuff in order to minimize the, I mean, the negative terms and all those things. Error would be your predicted value minus actual value. That would be the error factor. So the cost function is to minimize the error and make the model better. If error is more, right, the model is not significant. Every time you feed in cat, it is predicting dog or something else, right? So you need to minimize the error factor. That is where you use the cost function in order to minimize the error. This has been explained here. For an example, you have one of the data set called MNIST, right? MNIST is one of the data set which consists of handwritten images. Let's say people want to recognize the handwritten. What is this? So all the data set for each individual character and its label. Let's say this is an image of one and it is labeled as this is a one, a text class, text one, and this is the image, right? Those things are there in this particular data, MNIST data set. So what you're doing is you're predicting the 10 digits, 1 to 10, right? 0 to 9, sorry. 0 to 9 values you are predicting, okay? This is your different classes to be classified, the Y values. And in order to learn from there, you created various neurons, I mean the hidden layer of, we are putting the architecture of a neural network, okay? Where the outcomes are your these values, probably 10, whatever the neurons, right? These will be internally connected. All the weights would be associated with that, right? Then you have an input layer. This is your input layer, which consists of images. This is one bias stuff. So these value with each neuron is connected to various other stuff. Then the equation for this would goes as summation of all the weights I involved in that, and the number of uh, X items are present, right? Plus the biases, this one. This is your Z value, right? This is the Z value, and you apply on top of this, you apply some sigmoid or ReLU or so that it will give you 1 or 0 or range of -1 to 1 values. Those things are available at this point. This would go as saying that, let's say I passed in an image called 3, okay? Probably whatever the index generated by pixel values and all those things, the vector is this one. So at this point, you may get 0, 1, 125, 125, and all those things, right? This is the pixels associated with image called 3. Those goes here, it learns that, and it points it to this one, saying that this should be ignited. This should be ignited, or the probability at this point should be more than 0 0.5 or so. I mean, not 5, it is close to 1. So 8 or 9 or something like that. It should come across like this. 0.8. Other would be like with probability of 0 0.01, 0 0.02, 0 point, probably, which computes all our probability to be 1, 1.0, right? So at this point, whenever you get the highest or above threshold value, let's say your threshold is if it is more than the value comes in more than zero point 0.7 or so, then you say that it is associated value as 1, which is in our case the third uh, perceptron is active, which indicates that the matrix has 0 0 1 0 0 0 0 like that, which counts out to be 1 0 1 2 3 4 5 6 and all, and then it ignites this third bit, which says that you have inputted an image called 3 and you're getting the output as 3 like that. Okay, this is actually a simple architecture of neural network. It is a bit complicated, but need to understand the level. If you understand for sure, image would be in this format, and each perceptron has this equation, and each equation has an activation function for it, which converts zeros or one or in the range of 1 to -1. Then it goes on to the last layer, which specify that whichever is active or whichever is having more probability, then it will point out to that particular thing. Sometimes there will be incorrect values. Loss can be done, or the improper prediction will happen because of the training and all those things. That is what your cost function is. Lower the cost function, better the neural network. Right? You need to minimize the cost function. If you minimize that, it will be very efficient enough and your model would train it in a perfect fashion. There are a lot of other cost functions available, cross entropy, log loss, mean square error, all those things are available. So I've just listed out those. What it does is it takes the summation of, I mean, all the number of elements that are involved in this. Let's say these many perceptrons are available or the predictions are there. For that, it will take the summation of all those y value predicted minus the actual value. Predicted is your y hat, actually they represent like this. The prediction value will be always represented as y hat. I just make it as underscore because it would not have any stuff there. So y is your predicted value minus the actual value, which is same as your cost function. And then for mean square error, you have this particular formula. For cross entropy, you have this value. This is your predicted value. This is your actual value. So you use natural log here in order to reduce the non-linearity and all those things. For that, you use cross entropy function here. And when you're using binary class classification problems, probably people use cross entropy and binary threshold cross entropy and all those things people use. Right? We need to be aware of all those functions when to use what, or else at least be aware of what things are there for a particular function. Okay. So far so good. We will have a quick round of discussion because been talking me. So what happens is when you feel that it is like the outputs are not correct, what you do, you back propagate to adjust the weights. At the beginning, what happens at the beginning, these weights you see, right? The weights are initialized dynamically. Probably at the initial stage, the assignment of weights would be at random, 0 to 1, right? Those values will be there. Probably what we do at the initial stage, we will provide there are various other ways to give the weights. You can do dynamically, I mean randomly, or you can specify some initial weight as all unique as 1, all of them to be 1. At that point of time, significance of all would be the same. Then you get some error. You back propagate to adjust this one. Instead of 1, it should be something around zero point 0.2. This should be 0.35 or something like that, which cumulatively should be 1 like that, right? You adjust the weights. Neural nets is more about adjusting the weight, and the way you store this, right, as your model, what you do, you save each weight associated to that. The next time you feed in another image or so, you put in the weights associated with each value, and then you get an output. Same architecture would remain same, and the activation things would remain same. The most important is the weights, how best at it has been trained, the weights are adjusted, all those things. Based on that, you get the values there. Okay. So we do back propagate in order to adjust the weight. Instead of being 1, we back propagate saying that this was an error. Go back, adjust yourself using gradient descent. This is how change in z value with another, I mean, because of the output, you need to adjust the weights associated with these each perceptron, right? That is what the various compute the gradient actually. Gradient descent and all those things would take care. So in order to reduce the cost, we do back propagate. So how do we do that? Let's say for an example, you in gradient descent, what happens is you are at this point and there is a huge loss, right? There is the first time you build the first iteration actually. First iteration is the one where you traverse from beginning from this point to your y value. Okay. Then you try adjusting the weights. This is your back propagation. Then this is your entirely epoch, one epoch, right? One epoch is this one. You do a forward propagation, you come back. There are a lot of errors there. This is first stage, right? First stage. The next you learn from that. You learn from that. You try to get better at each iteration. You try to get better at each iteration. You find that loss has drastically reduced. And if you still fine tune that the model, right? Sometimes the error would increase, right? This is the plot of like learning rate versus the loss factor actually. The way it comes at that this is the minimal error factor which is coming. Error is tried to be minimized is your cost function. That point of time you reach the global minimum. Actually, these are two figures which talks about like a smooth gradient, a rough gradient. Gradient in the sense where you find sometimes loss here to be minimal and then it increases and all those things. You have your local minima and global minima issues in this one, in the rough gradients. So what happens is it comes down here and it sees whenever it sees that the loss is increasing, it stop by and says that this is my final solution, right? In this thing, it is fine. This is the small smoothest one. This is fine. But in case it started from here descending, okay, it found out this one as your best path because going from this cliff, it is increasing. If I further go here, it increases the error factor. Okay. Sometimes in order to learn this, I mean the error factor tries to get you need to you eventually know that the error would be very minimal at this point, but at the time of computation you feel that this is your final solution. This is the problem of your local minima. This is your local minima problem. Okay. This is your global. Actually, there are two terms in it. In gradient descent, this is your global minima. Okay. There are two things, global minima and local minima. Local minima, you find that when you iterate through stuff, you stop by saying that this is the best solution I got. But because of the learning rate and momentum, you know that there are a lot of other values in it, and you can descend more in order to reduce the uh, loss as such. Okay, you use learning rate and momentum in order to try out all these things. That's where you use hyperparameter as learning rate and momentum. Okay, so you use that the momentum. It will tries to make you out instead of being at the local minima. You come out there, you try out other stuff, and you came here. And then that point of time, you feel that this is your final result. But it was a local minimum. You have another stuff. Based on the learning rate and momentum, it decides that whether it will be having more um, um, cliff or probably another local minima will be there or not. Whether I have reached a global minima or not, based on the learning rate and momentum, right? Which are hyperparameters for that. So this should be very less 0.2 to 0.1, and this should be in the range of 0 to 1. All those things are there. So these are the fine tuning parameters for this. Okay. So once it reach there, you find the best solution where the loss is very less. Okay. That is what you do gradient descent. Each time you descent in order to reduce that error factor in a gradient. This is what your gradient. You're trying to descent in order to get the best result, right? That is associated with your differentiation. The cost factor to be differentiated and all those things. Error factors are then back propagated to the hidden layer. These will alter those weights. These values are associated with this, and then the weights are propagated back, adjusted, and then multiplied with the input values. Then it will try to go back from, I mean, it takes a forward propagation. It learns that, and then it back propagate, and it try to reduce the loss. Actually, if you plot this each levels of losses, right? The beginning you get lot of loss, and then you descend from there, and you descend from there, and you try. After some point of time, you get normal loss, which will be like this. So your loss function will be something like this. This is your best epoch. The number of iterations you do, for going forward and backward, this would be your best epoch to be taken care. That we will learn when we do practical stuff. You need to understand these terminologies, right? That is what I was introducing with variance. These are the hyperparameter for a neural network. Hyperparameter are those with which you can, it's like you are having a radio, you tune the frequency in order to get a better FM frequency, catching the frequency, right? That is what you say hyperparameter to tune a neural network. Okay. These are the one. Your learning rate, momentum, epoch, which we talked about. Learning rate is how quickly a neural network abandons the old beliefs for the new one. I mean, the way it tries to forget the older one and tries to learn the new one is your hidden understanding of your learning rate. Momentum parameter which helps to come out of the local minima and smooth out the jumps from here and there. When you look for the gradient descent, right? If at all it is like this, it will go zigzag like this. If the momentum is very high, it will go here, it will come here, and these that zigzag, it does that. So in order to make a smooth learning, you need to maintain a minimum of learning rate so that it forgets lesser value, older values, and takes new as much as minimum so that it will not go here and there. And then momentum factor in order to have a smooth jumps. Then it will learn appropriately. Epochs, as we know, a complete forward and backward propagation is your, to correct the weights, is your epoch. As the epoch increases, loss decreases. Right? That is how you look for your this stuff, error factor decreasing. Right? As the epoch increases, your error would decrease. Okay, that's the thing. Instead of having prediction to be image of 3, it is predicting as 2. That point of time, your classification error is there, right? Once you have given an image 3, and being the human, you know that this is 3. Your label is fine because your weights. If you consider the human understanding why it is 3, I'll just pull it out like this in my um, way. Let's say this is your 3 value. Okay, we know that as a human, when it has this curve, and this curve, for us in our brain, some weights are associated with this line, and weights are associated with this line. When it turns this way, we say that it is 3 because we are learned this that this pattern is turned out to be 3. Similarly, similarly, computer will understand these stuff and the weights associated with that. Strikes is like this. It understands that and it will label it as 3. Sometimes it may label incorrectly as 2, probably, which is wrong, right? That is your error factor. It has to be it has to be 3 actual value minus it was 2. Let's say this is your error factor. It back propagates in order to update the weights, right? It back propagates in order to update the weights. Uh, for the Ishan's question, do we need to memorize the formula for back propagation and all? No need to do that because there are a lot of libraries available. Okay, which gives you optimization, back propagation, what to use, cross entropy, and all those things. You need to be you need to be aware that these formulas makes it back propagation. At least understand the hidden formulas associated with that. No need to worry about these stuffs in detail to understand the formulas, remember all those things. But when you're doing coding in TensorFlow, you need to at least remember this. Calling this cross entropy would be suffice for your formula. Okay, and need to understand why rectified linear unit, why TensorFlow tan h, what is the significance of your sigmoid. These three are very important activation functions. Each neuron will be activated based on whatever the functions are there. Okay. Each neuron will be activated with some activation function. Either maybe sigmoid or ReLU, sigmoid or ReLU or tan H, right? Whatever might be. Based on the coding you do, it will be activated with these stuff. Generally people use ReLU. It depends on whatever we are doing. Okay. This is how the architecture would look like. If you add another layer, it will be multi-layer perceptron, MLP, right? Multi-layer perceptron. You know that. And you have deep learning, right? Another stuff is your deep learning. When you have more than one layer or more than one or two layers, right? Two layers, you call that architecture as deep learning. This is a simple neural net, okay, which is consisting of only one hidden layer. If you have such n number of hidden layers and then you have your output, then you call it as your, this architecture will be called as deep learning. Okay, when you have multiple layers, hidden layers, such like this, and you have the outcomes here. This is the input layer, this is the output layer, and in between you have multiple layers in it. Such things are called to be as your multiple layer perceptron or deep learning, right? You can say that. That is what the difference between your simple artificial neural nets and deep learning.
I'm sure you enjoyed learning from this video. Please like the video, and if you have any doubts regarding this video, please comment us in the comment section, and don't forget to subscribe to our channel for more such informative videos. Do look out for other related videos in our playlist. For more information, visit our website now. Keep learning with Intellipaat.